Right. So first of all, a very a warm thank you to Annabelle for organizing this, for Terry as well. And as they both mentioned, I was last at VKI, what seems a lifetime ago now, owing to coronavirus. But yeah, although I'm not there with you physically, virtually I am. So I put together some slides documenting some of the research that my team and I have been engaged in. It's a combination of machine learning, statistics, and largely aerothermal dynamics. I haven't gone, well, there's a bit of detail on the statistical side, but not as much as one would usually have for a statistical audience. So I've tried to do justice to both disciplines. Hopefully I don't fall too short of that goal. So yeah, without further ado, let's just dive right in. So in this talk, I'm going to be talking about two main case studies, as Annabelle had introduced before. One deals with Schlieren, and another one deals with measurements that we get from jet engines. Now, prior to delving into those two and the motivations for delving into those two, I want to give you a very high-level overview of something called Gaussian process models. And hopefully, if you all haven't studied it, you've at least heard of it in passing. So that's going to be the introduction, a high-level overview into Gaussian process models. Then I'm going to give you a very brief note of what I think as the change in the aerothermal measurement landscape. So the way we actually, not only the way we obtain aerothermal measurements, and so when I say aerothermal measurements, I'm primarily focused on pressure, temperature, density, velocity, etc. So not only the way we obtain those measurements from the sensor perspective, but also the way we process the data that's coming from those sensors. And then concurrently, how recent developments in other fields, notably computer vision and machine learning, have now put us at a stage where things we ordinarily wouldn't consider to be sensors can actually be perceived to be sensors. So a lot more detail on that later on, but just to begin, we'll start off very lightly with Gaussian process models, and then delve into some of the more aerothermal topics. Okay, so I'd like to begin this with a control volume, right? So on the screen, you see a control volume, which is effectively a square. And since it's plotted in 2 dimensions, I have the X and the Y axes over there. So let's assume, hypothetically, that we have access to some pressure measurement. So at a specific value of X and Y, at these coordinates, I have a pressure measurement. But for those of you who are familiar with measurement paraphernalia, and indeed the measurement chain, you never actually have a single value for pressure. Pressure will have some variability, and that variability can be associated with either the imprecision of the sensor itself, or perhaps owing to the uncertainty in the calibration that you apply when converting from millivolts to PSI, or just the fact that there is an ambient pressure that you typically require in order to do the calibration. That ambient pressure has its own uncertainty. So regardless of the source of uncertainty, I think it's a given that when you take a measurement, you will have some uncertainty, as shown here. Now, in what you're about to see, we're not really concerned with isolated measurements. Typically, the measurements that I'll be looking at in this presentation revolve around having 1 or 2 measurements. In fact, for most of the slides, it's more than 2. And so we have another pressure measurement here, as you can see in this control volume, denoted by P2, and you observe that there's a slight difference in the variance. And that could be for any number of factors, but a really simple one could just be that these measurements are taken with different sensors. I know for a fact that there is some underlying correlation or some relationship between the pressures at any 2 points within this control volume. But the challenge is I don't know precisely what that is. Now, in an ideal world, I could solve the Navier-Stokes equations and obtain the entire pressure field. And the hope is that it would corroborate well with my 2 pressure measurements. So the simulation or the model pressure at those two values of interest would be equivalent to the pressure that I'm actually measuring. But as you all are well aware, we aren't in a world where we have analytical solutions for the Navier-Stokes for high Reynolds number flow regimes that are of interest. And so we're left with this conundrum where we have these two pressure measurements. We know that there's a spatial relationship between them, but we can't prescribe that precisely for a regime of Reynolds and Mach numbers of interest. Okay, so what I can say is that there exists some function, right? So there's some relationship between the pressure at these 2 points, and I'm going to try to express that relationship between these 2 points using what I call a 2-point scalar valued covariance function. Now, what this effectively means is that if you give k the coordinates of these 2 points, namely the locations of P1 and P2, you effectively get a scalar value that comes out. And that scalar value can be used to represent the relationship between 2 points in space with respect to the pressure. So we think of this in the Gaussian process parlance as a kernel function that is characterized by some hyperparameters. So in addition to being functions of x, x prime, y, y prime, and the primes here basically denote the other point. We have a kernel function that characterizes the relationship, and that kernel function in itself is parameterized by certain quote-unquote hyperparameters. So there are two main points to note here. First is the assumption that there exists this kernel function, right? And that has a certain parametric form. And the second is that what underscores this kernel function are some hyperparameters which presumably give it some degree of flexibility in terms of dictating the relationship between the pressure at 2 points in space. So just to summarize, we can interpret the pressure within this control volume as effectively a Gaussian random field. Now, what that effectively means is that if you probe the pressure at any point in this control volume, so not just where you have the measurements, but more importantly, where you do not have the measurements, we're basically making the statement that the pressure at any point is given by a Gaussian distribution, i.e. it has a certain mean and it has a certain variance, right? And that variance is effectively coming from the fact that each point within this control volume satisfies or all the points in this control volume satisfy a certain covariance structure. And that's the key thing, because that covariance structure is effectively what's building the relationship between the different points, more specifically the pressure between point 1 and point 2. Okay, so there's a little more notation, so please bear with for those of you who are unfamiliar with Gaussian processes, but things it'll start to pick up and start to get a little interesting. It's just, we have to go through a bit of notation and math before we get to the interesting bits. Okay, we're going to stick with the same example as before, just because it's relatively simple and it's two-dimensional, right? So we effectively have pressure values that are coming from two sensors that we place within this control volume, and we define this in terms of a training data set. So x would basically be the two coordinates, so x1, y1, and x2, y2, and then f would be the means of those two pressure values. Now, what I'm interested in doing, and this is a theme that will run throughout this presentation, is I'm interested in determining what the pressure will be at all the remaining points. And we'd like to do this in a Gaussian process manner, which, as I mentioned before, makes the assumption that the pressure at any point in this control volume can be defined by a certain mean and a certain variance. So the way we formally define this is we define a joint zero mean Gaussian distribution, right? So we basically define a Gaussian distribution that takes in our training data and takes in our prediction points, i.e. the points where we wish to determine what the pressure is. We put them together in what we call a joint distribution. So for those of you who haven't seen this kind of notation before, this is relatively standard from the perspective of taking two quantities that you know are Gaussian and trying to determine what those two quantities together, what their joint distribution looks like. So we're going to spend a little more time just to make sure we all understand the notation. So we have this distribution, right? So the zeros correspond to the zero mean, and everything on the right-hand side corresponds to the covariance matrix. More specifically, you can break this covariance matrix, this large covariance matrix, into chunks. And so there's this block associated with the training data. So Cx comma x is effectively, well, do you know what? Let me hold on. I'm not going to tell you what Cx comma x is just yet, but all you need to understand is that it takes in the training data, right? So Cx comma x takes in the training data, as you see over there. And the sigma is effectively the noise, so the uncertainty or the variance associated with the pressure values, that's represented by this noise sigma. We have the prediction points that's characterized by Cx star comma x star. So that forms a block in this covariance matrix. And then we have the off diagonal, so the covariance between the training data and the prediction points. Now, I'm a very visual person, so I like to actually get, I understand equations better if I have pictures associated with them. So this is perhaps more for me than for you. So here's a picture representing what you see over here. So the training data, because we only have 2 pressure points, it's a 2x2 covariance matrix. And depending on the number of prediction points you have, you automatically decide what the size of the other matrices should be. Now, let's talk a bit about what exactly Cx comma x or Cx comma x star is. So once again, just remember from before, we defined training data and a set of points at which we require the pressure values, right? So x and x star. And so what's happening here is each element of the covariance matrix that you see is effectively that scalar value from this kernel function we used before, right? So we're saying that there's some 2-point scalar covariance function that defines the relationship between the pressure at any 2 points, and we're saying that provided you have that, you know what its hyperparameters are, you effectively evaluate your covariance matrix by taking the corresponding xi, yi, and x star, y star pairs, and you plug them into your covariance matrix as you see over there. Okay, so just a few more equations, and so these are effectively what we want. So what exactly we want is the value of the pressure at all the remaining nodes, i.e. at the prediction points characterized by f star and x star. So naturally, because everything is Gaussian, recall what we said earlier, that every point in this domain has a pressure value that has a certain mean and a certain variance. And so if I'm interested in that distribution across all the points, effectively I'm looking for the mean of f star and the covariance in f star. And those are given by these expressions. Now these expressions are simply a consequence of the fact that you've constructed this joined Gaussian distribution, and then you're taking, you're trying to determine what this conditional distribution is associated with f star conditioned upon f. The way I try to read this is that I'm trying to determine what the pressure is at the points x star, given conditioned upon the pressures I'm observing at x, right? So that's a simple way to interpret these 2 expressions. There is a Bayesian interpretation to all this, and once again, I won't go into too much detail. I'll try to keep things as general as possible. So what the Bayesian interpretation of all of this is the following. It's that at the end of the day, you see f, right? So this is what we actually measure, but the truth isn't exactly what we measure, right? Because as I said before, for a variety of different reasons, your measurements are corrupted by some sort of a noise. And so the truth is what we don't know. And so just based on this expression, we've basically determined what our noise or our likelihood is, or some people often refer to this as the noise model or the likelihood model. So this is effectively the likelihood within the framework of Bayesian inference. So our likelihood is defined by our observations and the noise. And then the kernel function that I mentioned before, the one that is parameterized by certain hyperparameters, that effectively sets our prior. So we say that our prior is given by P of T of X, which is effectively, once again, a zero-mean Gaussian distribution, but has a certain covariance structure, and that's based entirely on where you're actually getting your measurements from spatially. And at the end of the day, what we want to infer is a posterior. So we want to determine what the distributions of the unknown hyperparameters, in this case, alpha and L. So just to recap, because it's been a few slides, I said that we're going to make the assumption that this two-point covariance function effectively is given by some parametric form. And that parametric form is underscored by two hyperparameters that we don't precisely know. So the central objective of this Bayesian inference is to determine what the posterior distributions of the alpha and the L's are. And by doing so, we'll also determine what the distribution of pressure is within this control volume. And an intuitive way to think about all this is you effectively have a distribution associated with this quantity here, right? And you're trying to identify the full distribution of this by randomly picking samples from alpha and L, because these are the only two unknowns in what we've seen so far, right? We do not know what these two are precisely. And the way this is typically done within a Bayesian inference framework is that we'd assign these some prior distributions as well. So I can just say alpha is just a standard normal distribution, and maybe L is a Cauchy distribution. And then based on generating samples from these distributions, we then try to figure out what will maximize this with the objective of trying to recover the full distribution. So hopefully that made a bit of sense. If not to worry. In the slides that follow, I'll try to reiterate some of the underpinning concepts that you've seen so far. And with that, I'm happy to say that's pretty much all the heavy math. The rest of the content of this presentation is basically about applications of the mathematics that you've just seen. So as promised, a very brief note on what I see as changes in the aerothermal measurement landscape, and more importantly, why I think Gaussian process models have a very powerful role to play within the aerothermal measurement landscape. So the first one is that over the last decade, and arguably even 2 decades, we've seen advances in MEMS technologies that have permitted the development, the fabrication of much smaller sensors. Now, what that means is that you can place your sensor, now here I'm thinking about temperature pressure sensors, much closer to where you're taking the measurement, and that will result in a faster frequency response. So from the perspective of, say, gas turbines, that effectively means you can run your experiments much more faster rather than waiting for, because there'll be a certain lag between when you actually reach a certain temperature and when your sensor measures that temperature. And by placing the sensor closer to the actual probe head, you're able to increase the frequency response, thus accelerating the pace of your experiments. Point number 2 pertains to rapid prototyping and novel materials. So this permits us to design probes that are extremely small. So for instance, when we started looking at modern keel probes for temperature measurements or indeed pressure measurements, these are now of the order of have a diameter of less than 1 millimeter, which is incredible. And what this permits is extremely non-invasive measurements within the flow field. The 2 other changes that have actually resulted from, I suppose, work in different fields is the rise of uncertainty quantification research. So this is something that undoubtedly all of you are familiar with. There's been quite a bit of work on UQ within CFD and computational models. And there's also been a bit of work, but perhaps not as much, on experiments, i.e. how do we come up with new ways to perform uncertainty budgets. And when I say uncertainty budgets, you can effectively think of it as the aggregation of all the individual uncertainties when you conduct or carry out these large complex experiments. And finally, the 4th point, and one that I find particularly interesting from a research perspective, is the rise of I mean, it's called many names now, AI, machine learning, but loosely stated, the acceleration of tools within these fields has offered pathways to transform what we previously thought of as simply qualitative data into quantitative ones. A really good example of this is some work that was done in Caltech, where they wanted to determine wind velocities over a wind farm. And rather than place anemometers throughout the wind farm, what they ended up doing was they took pictures, or videos rather, of flags that were moving around the wind farm. And based on the movement of the flags and a bit of calibration, they were able to determine what the wind velocity and direction was, which is obviously really, really cool. So here are my two research questions of interest. So the first one is, how do we extract quantitative information from old Schlieren images? And so here's an example of a Schlieren image for a T-38 aircraft. So this is from NASA. And the second one is, how do we calculate the efficiency of a jet engine? Now, there are many ways to think about the efficiency of a jet engine. What I'm specifically interested in is the breakdown of that efficiency. So now, one can argue that efficiency is a relatively well understood concept when it comes to a jet engine. You simply determine how much fuel you're putting in, how much thrust comes out, but it's the breakdown of that propulsive / multiplied by thermal efficiency into its different components that is much more challenging to determine. So for instance, if I wanted to ascertain what the efficiency of only the high pressure compressor was, that problem is a lot harder compared to understanding the efficiency of the entire power plant. And I'll explain why as we continue. Okay, so there are papers associated with these two works. The first one pertains to stuff that has recently come out at AIAA. It's called Quantitative Schlieren Using Gaussian Processes. So as I'm sure all of you are familiar with, Schlieren is effectively exploiting the refraction properties associated with light in a specific medium. More specifically, if you have a light from point source where the rays are collimated and it's passed through a specific test section using two convex lenses, you observe these refractions, which are an artifact of density variations within the test area. And these refractions can be projected on a screen once they pass through a certain knife edge. And what the knife edge does is it determines the direction of the refractive index that's captured. So if you have a horizontal knife edge, you're effectively going to capture refractive index variations along the horizontal axis. And if you have a vertical knife edge, you're going to capture refractive index gradients along the vertical direction. There's a similar idea behind shadow graph, except for the fact that the distinction between Schlieren and shadow graph is that with shadow graph you're looking at the second derivative, whereas with Schlieren you're primarily interested in the first derivative. I'm going to be a little more precise in the next few slides about what I mean by all this. So you can think of a Schlieren image as effectively the refractive index gradient along a particular direction, where, as I mentioned, the direction is determined by the orientation of the knife edge. Now, there's this really nice classical linear relationship between the refractive index and density, and this is characterized by the Gladstone-Dale coefficient, as you see on the screen there. Now, there are any number of quantitative approaches for extracting density values from Schlieren. So background-oriented Schlieren is just one approach. But it's fair to say that it requires both an extensive knowledge of the flow as well as a modification and detailed understanding of the Schlieren apparatus that's actually used for taking the images. Now, what we want to do, as I alluded to earlier in the title, was that we want to be able to go back to old Schlieren images and be able to quantify them. More specifically, extract density contours from these old Schlieren images. And we're proposing to use Gaussian processes for this task. Now, a Schlieren image, as all grayscale images, is effectively a series of pixels that have values between 0 and 255, as you see on the screen. And so effectively what we need is a transformation. So we're going to transform from what I'd like to call Schlieren, which is 0 to 255, so these are the pixel values, to a scale density. So you notice that we're going from d tilde rho to rho. And then finally from scale density to density, which obviously is rho. Using the same expressions from earlier, we're going to define our f. So these correspond to our, from before, this is where this would have corresponded to pressure measurements, whereas now they correspond to Schlieren measurements, if you will, which are values between 0 and 255. We're going to try to map from Schlieren to scale density, but using the same Gaussian process machinery. So recall what we had before. So that's the first equation that you see over there. So that shouldn't be new. But the second equation below that, where we have, if you can see my cursor, where we have this joint distribution now, what we've done quite simply is just take the gradient. So it's actually the derivative because it's a gradient along just the x direction. And when you do that, you effectively get this formulation. Now the caveat, of course, is that the kernel, when you define this operator, you're effectively taking the derivative of this kernel function, so the same one we had before, along the x direction at each entry or each index of these matrices, right? So that's the simple trick. And this isn't necessarily new. So this is also known as derivative enhanced Kriging. It's known as derivative or gradient enhanced Gaussian process models. So this is something that is a well-known idea within the Gaussian process literature. But the only change we're making is that we're using this on Schlieren as opposed to just pressure values. So here's the step-by-step workflow. And once again, I'm going to rush over a few details in the interest of time, but feel free to ask questions later on. So we select a Schlieren image, and what you see over here is effectively a shock wave that's forming across this this edge. And the next step is to sample this image. So as mentioned before, as you sample this image, effectively you're collecting samples of f, which in this case would be the Schlieren. We pass these Schlieren values through our Gaussian process model, the gradient enhanced one, to arrive at f star, which corresponds to our scale density. And I say scaled, as you can see from the values on the color bar. This range varies because it's dictated entirely by the Gaussian process model. Now, to convert from the scale density to density, we require an estimate of the true density, at least at 2 points. So if you have the inlet density and the exit density, we're able to adjust linearly. And then we arrive at the distribution you see on the far right-hand side. Just to compare, what you see is the, well, I say true density, but effectively this is an estimate at best, because this is coming from background or oriented Schlieren. So what you see on the left is the truth, and what you see on the right is the mean. And I also show you the standard deviation, which effectively is an assessment of the uncertainty in the model, given the workflow that we used. So it's capturing a lot of the right features. You can definitely see that it's getting that leading edge bow wave over there. It's seeing this characteristic shock behavior over there. But there's certain things it's not quite able to capture. So for instance, you see this variation in the density over here that we don't report over there. Now, once again, it could also be an artifact of the uncertainty present in the background oriented Schlieren as well. So once again, just to contrast, this is, if we go back a slide, you can see the distinction between the original Schlieren image and the density estimate on the far right. So it's not just a linear scaling of this, it's a linear scaling, which is the final step, but the more important step is that conversion or that mapping from the gradient to to tilde rho. So the initial results are very promising, and we've tried this on a few more applications with similar successes. But there are a lot more. We feel that we're just scratching the surface in this respect, because this is really exciting. Because you can imagine, you can go back to a lot of old historical Schlieren images, and you can start to work out what the true density values in those Schlieren images is. And more importantly, we're trying to do this as best as possible in a very principled manner. So we also have an estimate of the uncertainty that's coming out of this model. So in terms of ongoing and future directions, we're identifying cases where this linear scaling doesn't quite hold. So that effectively means that the density variation in the other direction is very nonlinear. And what approaches we can develop to mitigate this. Then there's also this question that we're still working on, actually. It's if you can use edge detection approaches to determine what the shock angles are, and then go back to theta beta Mach number tables to work out effectively what the density is. Well, inlet Mach number and then subsequently the density. And we're looking at cases where we have images, Schlieren images, the same test section, but under different knife edge orientations. And then finally, looking at different physics-driven kernel approaches that we can use for better capturing some of the shocks and plumes and other physical characteristics that we see in a lot of Schlieren images. Right, in the interest of time, I'm going to go a bit faster through the second case study, which is how we calculate subsystem efficiencies of an engine. But what you'll notice, and I suppose the underlying theme of this case study as well, is the use of Gaussian process models. But as you will see here, used in a slightly different way. So for the Schlieren, we derived a gradient enhanced version of your standard GP model, whereas here we're going to do something different, but more on the kernel side than the actual structure of the joint distribution. Once again, this is work that's actually been going on for several years with Rolls-Royce. So there is a very strong industrial interest in what I'm about to share with you. Okay, so just a bit of a bit of scene setting, if you will. Accurate performance metrics such as component efficiencies require accurate measurements. And although there's been a tremendous body of work dedicated to quantifying uncertainties within fluid simulations, it's challenging to deploy that body of research to experiments just because of the very nature of experiments. They're noisy, they're sparse, and possibly erroneous. Now, what we're interested in is computing subsystem efficiency. You can think of the efficiency, let's just say, of the high-pressure compressor as being a function of inlet and outlet stagnation quantities, i.e. inlet and outlet stagnation temperatures and pressures. Now, in an engine, we don't get mixed out averages or even mass averages. We typically just have area averages. And these come from, or an assessment of these area averages is made based on the composite sensor values. So across a given measurement plane, we'll have a series of different rakes, and from these rakes, we're trying to infer the average temperature and pressure. And you see, this is kind of a simple schematic of what that would look like, right? So it's slightly scaled, obviously, but you do see a few rakes, so 6 rakes, each with 7 probes, giving you different values of temperature. Now, a little more scene setting. So averaging practices for estimating quantities typically vary from simple averages. So you actually just take kind of an ensemble average, if you will, or more refined sector-weighted averages. So basically, you work out what the sector coverage of each probe is, and you weight it accordingly. So what that would imply is probes towards the casing would have far more weight compared to probes at the hub, just because of the sector area they cover. Now, for reasons that will become apparent shortly, these aren't really tailored for spatially non-uniform flows. So a simple way to think about that is if you're taking measurements of something that's varying harmonically, which is typically what you find in an engine, because you have effectively upstream blade rows and upstream components. So you do have a harmonic variation in both pressure and temperature. Now, depending on where your instrumentation is placed, you might either capture the trough, or there's a risk rather, you might capture either the peak or the trough of such a waveform. And so you can end up with an estimate that's very biased just based on where you place your instrumentation. So that's one risk with current averaging practices. Another issue is just the way we aggregate uncertainties. So what's typically done and recommended, and when I say recommended, I refer both to this AGARD AR245 report and also the ASME performance test code. In terms of the way you bookkeep the uncertainties is you try as best as possible to estimate what the standard deviation is, and the correlation between the different sources of uncertainty, and then you aggregate them in kind of the standard rudimentary framework that you would use. So you sum up all your standard deviations, and then you sum up the correlations as well. Now, my issue with this, and I'll argue why, is that this doesn't account for the fact that a very small uncertainty measurement can have a massive impact on your area average. Because if you measure something incorrectly, your interpretation of the entire spatial field can be significantly off depending on how sensitive the field is to that measurement. So with that in mind, it's also worth bearing in mind that there's a difference between rig tests and the real engine environment. And a lot of the CFD that we use is typically extremely well validated with rig experiments. But there is a difference between what we observe in the rig and what we observe in the engine. More specifically, the rig doesn't capture these engine modes. So things like casing ovalization, the impact of upstream bleeds, wakes associated with certain upstream struts, those are things you typically wouldn't observe on a rig. So here's the idea. We're going to approximate the spatial field of pressure or temperature in an engine, and then we're going to integrate. So the approximation step requires us to, once again, use a Gaussian process model. And the integration step requires us to be able to integrate this Gaussian process model, which is actually really easy, as I'll share with you shortly. Okay, so here's what we have. We have some measurements, as you see over there. And in the same fashion as before, we set up our training data. So we have our x's, which is basically a matrix of the r and theta values associated with these measurements. And then the f's correspond to in this case, the temperature values that we're getting from the different sensors. Now, this is where things get really interesting. So we're not just going to use a squared exponential kernel as before, primarily because you pick a kernel because it embodies some of the underlying physical characteristics that you wish to capture. So as I mentioned before, the kernel tries to relate any two different spatial locations, in this case over the annulus, so r and theta and r prime and theta prime. And this relation is developed in the absence of measurements, but with some physical insight. So we're going to express our kernel effectively as a product kernel. And we say that this product is formed by a kernel in the circumferential direction. So in the circumferential direction, what the driving phenomena in an engine is, are these modes. Whereas in the radial direction, you typically observe something that's akin to a spline. So for that, a radial kernel seems appropriate. So for the circumferential kernel, effectively, we're using something called a Fourier kernel. Now, with a Fourier kernel, the caveat is you need to be able to precisely state what the harmonics are. Now, that's a challenge because we don't know precisely what the harmonics are. So what we do is we set a range. So we'll say I expect harmonics 1 through 20. And sometimes we might even add a few higher modes as well. So for instance, I might expect 140 because I have 140 stator blades upstream. So we come up with some listing of these are the range of different harmonics we can expect. And we give each of those harmonics a certain prior, right? And the idea is that if the model really needs to use a specific mode, let's just say a mode 4, then it would pick that mode 4. But if it can explain the data without requiring a mode 4, then it doesn't use a mode 4. So that's kind of, at a high level, that's the basic idea. Okay, so just to get into this a little further, we take the measurements, we pump them through the model. As you can tell, in the circumferential direction, you start to see these harmonics present. So this is once again an artifact of the kernel we've used, and we also have an uncertainty associated with the spatial field. So this is just the mean and the standard deviation from this Gaussian distribution. And if you look at what's happening in the circumferential direction, in this case at a radial location of 0.8 millimeters, that's the variation you observe. So you can see it's capturing this harmonic behavior. And the radial direction, we get effectively this spline-like characteristic that you see over there. So I noticed there are a lot of questions. So what I'm going to try to do is I'll quickly rush through this, and then if it's all right with all of you, I'll address each of your questions in about 10 minutes. Or less than 10 minutes. Now, the nice thing about having this Gaussian distribution model is that you can analytically compute the integral. So we can compute the integral of this distribution, and when we do that, we get an area average. And this is quite a significant result, primarily because of the fact that to the best of our knowledge, it is the most rigorous way of determining what the area average is at a given measurement plane for either pressure and temperature. And this is something that's been really well received by Rolls-Royce because they really think that this is the way to go in terms of computing area averages in jet engines and in gas turbines based on the measurements that we have. I also want to emphasize why this approach is so different from classical techniques. So if you were to take any widely adopted strategy for area averaging, so in this case, I'm referring to the sector-weighted area average, where you average based on the sector coverage of each probe, for a temperature field where the harmonics were known, this is with uncertainty, of course, this is effectively a convergence result. And the convergence result is the area average does not converge. So as you go from left to right, we're increasing the number of rakes in an engine, and you don't observe an increase or decrease in the area average measurement. And the dots for a given number of rakes just correspond to different rake positions. So so let's just say for 4 rakes, I can have them at 0, 90, 180, 270, but obviously that doesn't make sense from the perspective of aliasing. So basically what I'm doing is I'm generating random rake placements and then figuring out what the area average is. Now, what you see on the right-hand side is a proposed Bayesian approach, and the main point to note is that you get a convergence, right? So beyond 10 rakes, you don't see that much of an uncertainty in the area average as compared to the current widely adopted strategy for area averaging. So this is also quite significant from the perspective of this Gaussian process framework. You get this convergence, which makes sense because as you add more instrumentation into an engine, you would expect a convergence in the area average. A few other points to note. This uncertainty can be decomposed. Now, what do I mean by that? When you think about an uncertainty, you have to think about it in terms of the perspective of the engineer. He or she needs to reduce the uncertainty at some level. And so the question really is twofold. Do I need to increase the number of rakes I have in an engine? Or more generally, do I need to increase the number of sensors I have in an engine? Or do I need to increase the fidelity of each sensor, i.e. increase or decrease the sensor uncertainty just because of the fact that a given temperature or pressure sensor has a certain nominal uncertainty associated with it? And this approach does that nicely because using what we call, it's a well-known statistical concept. It's called the Law of Total Covariance. So you can apply that within this Gaussian process framework to break down your overall uncertainty into uncertainty that's arising because of the fact that each sensor has a certain imprecision, which is called impact of measurement imprecision, and spatial sampling, which is you don't have enough sensors spatially. And you can see that over here on these two figures. So clearly from here, it seems that the by 2 orders of magnitude at the very least, the uncertainty is arising from the fact that we don't have enough circumferentially placed rakes. This is just as a side. If we only had one rake, this is what it would look like. So clearly here you see that all the uncertainty comes from spatial sampling. But also note the distribution, that where you have the measurements, the uncertainty is 0, which makes sense. But as you move away, we tend to have far greater uncertainty. Yeah, so this is why it's this kind of a breakdown is very important from the perspective of planning experimental design procedures for the next test that one wants to do. It's fair to say that the modeling framework is very robust. So if you did have missing measurements, which is something that happens, so either if you have anomalous measurements or if you have missing measurements, the framework can still cope and it can still give you an area average value, but obviously there'll be slightly larger uncertainty because you do have missing measurements. The final point I wanted to make was regarding the selection of the harmonics. I didn't delve into too much detail on this, but I did mention that when we construct a Fourier kernel, we effectively select a range of different harmonics. And then once we actually do inference, in this case using MCMC, Markov chain Monte Carlo, the chain effectively will tell us, it'll basically select the modes that it deems to be the ones that explain the data the best. Now, that's done from two perspectives. First of all, you have to interpolate the data, but you also want to make sure that the standard deviation, the model uncertainty, is as small as possible. So you're playing with these two things, and it's trying to find the best fit for the different parameters that have been selected. So in this case, we had frequency ranges from 1 to 12, and it's figured out that I need modes 1, 1, 3, and 12 more so than some of the other modes. So just by inspecting these hyperparameter marginals, you can determine which of the frequencies are dominant. Okay, so this is my last slide. Sorry, I've gone terribly over. In terms of ongoing work, what we're doing is we're extending this model in the axial direction. So we're not only looking at one measurement plane, but we're looking at, well, the latest version, we're looking at 8 different measurement planes at the same time. And using the data from 8 measurement planes, you get a better estimate of the area averages across the different measurement planes, which results in a better estimate of efficiency. And the other interesting thing we're doing is that we are using what's called transfer learning. So it's kind of a machine learning approach, or notion rather, where you transfer the knowledge learned from one model onto another. And so what we're doing here is obviously we have a lot of test engine data, or rather roll test engine data. We deploy the model on the test engine data, and we try to use what we learn from the test engine data to see if we can better understand what's happening in the air on engines that are currently flying. And the main difference is that typically the instrumentation that you'll have is far lower. So just because of weight constraints and measurement paraphernalia constraints, you would have far more instrumentation in an on-ground tested engine versus engines that fly in the air. So we're trying to see if we can learn more from what's happening on the ground to infer what's happening in the air. Okay, so with that, I'd like to thank you for your time, and apologies for running over. Should I take the questions now, or?
Thanks a lot, Pranay. I think so. I see that people are writing on the chat. Normally, I would just give the turn to the person. So I would say if Nassim wants to ask right now himself, he can ask. Otherwise, you can just read the question and answer him.
Okay, right. So I'll start from the top. Yeah, so that's so the question is perfectly valid. You can do it both ways. You don't necessarily have to. In what we did was we had density values as the input, but you can do it as you mentioned as well, and then integrate rather than differentiate. So that's perfectly fine. The main thing to note is that a Gaussian process, a linear operator that's acting on a Gaussian process will also give you a Gaussian process. And therefore, whether you integrate or differentiate, you still have a Gaussian process. So you can leverage all the expressions for computing or arriving at the conditional distributions that you want. So in our case, it was the conditional distribution of the quote unquote pseudo density conditioned upon observations of Schlieren or pseudo density gradient. Okay, next question.
I think most of them are about Schlieren. So Thierry,
okay, sure, yeah.
If you could comment on the development of the method to apply it to Schlieren movies to capture unsteady features.
So yeah, I mean that's a really exciting question because we were so the conception of this project started off with a page from Anderson's textbook. I was trying to look for it in my desk. Fundamentals of Aerodynamics. So in that, towards the end, you will see an image of a NACA airfoil in supersonic flow, but it shows you both the pressure distribution across the airfoil for different inlet levels of different inlet Mach number conditions, and you see the progression of the shock. And so there is this idea of, can we take in a video and then be able to apply the same approaches we're currently applying to an isolated image. The thing that I haven't been able to formulate clearly is how do we leverage the temporal change, because as you move each frame, you'd imagine that the position of the shock, or if you're looking at a jet, the distribution of the plume changes. So how can you best leverage the GP trained at one time step before to empower the current one? If you set that aside, the other challenge that we have right now is that this thing takes a lot of time, just because you're training a GP model on quite a huge number of points, and the number of points depends on the size of the image. Now, granted, you can obviously scale down the image or subsample it, but to get a really crisp density estimate, you have to use kind of a full resolution image, and that typically takes a few hours for us to run on a laptop. So I think in terms of being able to do this real time on a video, that might take a few more years of research, but if we treat each frame kind of in isolation almost, I'm fairly certain we should be able to do it for a video.
Thanks for your answer. Thanks for the talk.
Oh, sure. Then the next I think is Geoffrey, but this is also a question I have, which is all dealing with priors and everything. So how do you actually infer the hyperparameters of the kernels? And what kind of priors you impose? Because I guess that can be, depending on your measurements, that can quite bias your estimations.
Yeah, absolutely. And so here I'd say it's more of an art than a science to some extent. There's a lot of theory, and Andrew Gelman's book is a good resource for this, on using priors that are well informed versus priors that perhaps are not as informative as certain other priors. And so the classic example here is, instead of using a Cauchy prior for some parameters, use a half normal distribution. The other kind of artifact, the other point to bear in mind is that with priors, you have to, depending on the choice of the prior you use, you might end up with a covariance matrix that's not positive definite, right? And so that's the clear indication that, okay, maybe sampling from this prior distribution doesn't make sense if anything that's kind of less than 0, or this half of it, or the left half plane of the distribution, is going to give me a covariance matrix that's invalid, right? So that's another kind of clue that, okay, I need to change my prior. I think the challenge for us in terms of prior selection has been more with the jet engine project. And the reason I say that, and I tried to allude to that here. So hopefully, yes, you can still see my slides. So what we did here was we used something called a Finnish horseshoe prior, which is effectively, it's actually a series, it's a hierarchy of priors that you use to promote sparsity. So the idea is that, you know, it's almost like if you're solving there's an analog between what I'm about to describe and compressed sensing or sparse regression, where the idea is that you have maybe 20 different covariates, but you don't want to use all of them. You'd rather pick the fewest number of covariates possible to explain the data. And so it's a similar idea we use here, where we're saying that we want to be able to best characterize the circumferential variation in temperature, which is inherently sinusoidal, but to explain that sinusoid, that curve, which comprises of multiple modes usually and noise, we want to use the fewest number of we want to use the fewest number of modes as possible. And so by setting the sparse prior, so there's a wonderful paper on this. I think it's called the horseshoe prior, and then the Finnish horseshoe prior is an improvement of that. And it's called Finnish because it was done by researchers in Finland. But effectively, what you see there is a very principled way of trying to promote sparsity, but in a Bayesian way, as opposed to kind of the standard frequentist way where you're minimizing the L1 norm of over your covariates. So yeah, I think it's when you have to prescribe priors that are sparse or have some additional property or structure that they need to adhere to, then it gets a lot more interesting. In terms of the sampling, for everything that we've done here, we use no U-turn sampling, which is something that's kind of standard. This is a standard implementation of. It's basically an MCMC algorithm that calculates gradients as well, just to accelerate convergence. So this is something that's standard in PIME-C3, in I think even in STAN. So that's what we use for all the MCMC results. Hopefully, I've answered your question in a rather roundabout way.
Yeah, I think so. Yes. I think Olivier had a question that he might ask you about the Schlieren processing.
Oh yeah, yes. Yeah, was too lazy maybe to formulate, but thanks a lot for this lecture for this presentation. My question, in fact, regarding Schlieren, I'm used to Schlieren on both technique, and I was looking also how to, let's say, quantify that. But now I have a question. Maybe I not understood very well, but maybe you can enlighten a bit. So your technique is working fine in your case, and you have a 2D model. So the Schlieren is coming from a 2D model. Imagine you have an axisymmetric model. So, but what you see on your screen is a contrast, you know. So, and then you relate it. You relate it to the gradient of density. But in axisymmetric model, what you see is not directly the gradient of density, because the gradient of density is because you have a 2D, and then you can integrate along the line, the path of the optical path. But when you are axisymmetric, you are crossing different density gradients, and then you have to take the log of this density, and then it's different to interpret your Schlieren. So I don't know if your techniques could cope with that also, or is it something?
So we haven't looked at any axisymmetric cases yet. This is something that we're trying to do, but haven't been able to get the data yet. So if you do have like specific cases that you'd be happy to share with us, I'd be more than happy to
yes.
So that's one point. The second point is in terms of if you were to introduce a log operator, we would still probably be able to work with that within the Gaussian process framework that I mentioned. Obviously, there are additional sorts of uncertainties there, but it's definitely something we could do. I'd have to give it a little more thought, but I would think that there are enough bells and whistles in the framework within this Schlieren Gaussian process framework that you can account for these additional artifacts. So yeah, but to be brutally honest, I think it's one of those things that I'd have to look at the data and then try to code it up and then get back to you on.
Okay, thanks a lot. Thanks a lot. It's very extremely interesting. Thanks. I
have a last question, quick. How do you take the uncertainty or the imprecision? I don't like saying imprecision because imprecision to me is more like when you don't know exactly what the distribution is, so you are a bit imprecise. But the imprecision of your measurement is something that the experimentalists give to you. Like they say, okay, we measure the pressure within this kind of bounds, or is something you do yourself? Like they give you the raw data and then you somehow manage to.
So it's a combination. So we do have a look at the raw data, but because of the fact that there's so many additional calibrations, so if you just as an example, if you take if you were to take a temperature measurement in relatively high Mach number flow, just in isolation, so you just have a single temperature probe. If you look at the source of uncertainty, they range from uncertainties associated with recovery, the fact that there's some convection losses between the true stagnation temperature and what's actually measured at the probe head. There are uncertainties, depending on the temperature, of course, there might be uncertainties associated with conduction and radiation. And there's also the uncertainty in the calibration, right? Because this is effectively just measuring a delta, a change in millivolts, if you will. In order to determine what in order to basically convert it from millivolts to Kelvin, you need a cold junction temperature estimate, a cold junction temperature value, which also has some uncertainties. And so, with respect to your question, we don't do a lot of that processing. So we look at the raw data, we look at how the filtering is applied to remove the noise to, like, I think it's typically 50 to 60 and 400 harmonic hertz. And then we know to some extent what calibrations they apply, but in full disclosure, it's still very, very involved, especially for a real engine experiment to understand a lot of the bits that go in. So ultimately, we do get a precision estimate, but we're also able to get kind of the breakdown. Like this much of the uncertainty was associated with static calibration. This much was associated with the recovery. This much was associated with just the length of the wires. That creates a certain uncertainty as well. So yeah, it's one of those things that from a research standpoint, I'm looking to go further into, but it's also quite complex because, and it's something I never really appreciated before, is just that the complexity of these jet engine measurements is just phenomenal, and it's really tough to understand all the different pieces. So what we typically do is based on an estimate of, that's in full disclosure, it's not as rigorous as it can be. Based on an estimate of the imprecision for each probe, so effectively a sigma value, we use that, but then for each plane we'll have a slightly different sigma, because as you can imagine, if you measure temperature at the back end of the high pressure compressor, that uncertainty is very different to temperature you measure downstream of the fan, and that's just because the instrumentation is very different. Because at the back end of the compressor, you're looking at anywhere from 600 to 900 Kelvin. Back of the fan, you typically have close to ambient temperature values. So the instrumentation is different, so the sigmas are different, and that starts to become a lot more important when you, as I alluded to, when you have a multi-plane model, where you try to take measurements from multiple planes and fuse them all together in a single Gaussian process model.
Mm-hmm. And have you tried putting uncertainties to the uncertainties? Meaning learning, the standard deviation from your measurements with some prescribed prior.
Yeah, so we did that. so in kind of an early version of the model, we effectively assigned our sigma as a prior. And then the MCMC iterated on the value of sigma as well. But we struggled to get the MCMC to behave so that's kind of, I suppose, another issue of prior elicitation, that we found it's much more easier for us to prescribe a fixed sigma value rather than have the chain iterate over sigma, because you can get very, very different output values. And I think your chains will struggle when your output distributions are extremely multimodal based on the value of sigma. So that's one thing we did. We also tried a more simpler version of the model where we had kind of a hierarchical distribution associated with sigma. So you had two other priors that sit above sigma that then determine what sigma is. And that was kind of an attempt to emulate what's actually happening in reality with respect to how you aggregate all the uncertainties to come up with a single sigma for a given temperature pressure measurement. But that didn't really go too well either. So a lot of it is, I suppose, it's a combination of trying to be as rigorous as possible, but then also trying to get the MCMC to work and behave.
Mm-hmm. Okay. Well, thanks a lot. I think with this we can close the seminar. So whoever doesn't want to stay farther can go. And I think we can start the workshop, at least to get some taste of your library. And thanks a lot for the talk. That was super interesting, actually.
Sure, thank you. Right, so I have slides as well for this. So I guess I'll let me see if this works. So there's a lot more turbomachinery here than in the presentation before, but okay, hopefully you see some slides.
Yes, we do.
Okay, excellent. Right. So equadratures is a library that my team and I have been developing over the last 4 or 5 years now. And it initially started off as a library just for uncertainty quantification, but since then it's evolved into something a lot more. If you're interested in learning more about the code, if you just go to equadratures.org, so equadratures.org, that should basically take you to the website with all the information. Do you know what? I might as well share this as well. Sorry, I'm trying to do multiple things at the same time.
Don't worry. I would encourage people, maybe if you have direct questions this time, just unmute yourself and ask. You know, this is a workshop. I guess it's, you know, we can interact a bit more. So that's it.
Yeah, absolutely. Okay, so this is the main website. So simple enough. If you go here, you can check out the tutorials. You can check out documentation. My internet, as you can tell, is abysmal, so I'm not even going to try going to any one of these pages. And then you can also check out our Discourse Form. Now, the Discourse Form, which I'll talk a bit more about in detail later on, is something that I encourage all of you to join. So everything that you see here is free. It's open source. There's nothing inherently commercial about it. And if you go to the Discourse Forum, we do have some really interesting blog posts that really combine. I mean, we're all aerospace engineers at heart, so it's kind of a strong aerothermal focus and applications with different objectives, i.e. UQ, surrogate-based optimization, numerical integration, and dimension reduction. Now, with that, I am going to delve into this presentation, which effectively is a potpourri of sorts of different capabilities within the code. And I'm going to try as best as possible also to walk you through the research. So in terms of strategy, the research that we do as a group is split into stuff like the Bayesian work you just saw, and then there's a lot of the other stuff, which is what I'm going to share with you, which is also very, very exciting and interesting. Okay, so the true star of the show, if you can call it that, are these polynomials. And so effective quadratures through equadratures is built on polynomials. And we have a variety of different polynomials that you can build. So we have piecewise polynomials, we have subspace polynomials. So piecewise polynomials, obviously, if you have polynomials that need to be designed to be discontinuous in some sense. So you just have different phenomena, or the classic example I like to think of is if you're trying to model the CD over a cylinder with respect to Reynolds number, and if you look at that curve, although there's not an explicit discontinuity, it's not something that one would like to define using a single polynomial. You'd like to have, two polynomials, one for the laminar regime, one for the turbulent regime. So that's kind of a nice way to think about why you'd use piecewise polynomials. Subspace polynomials. So obviously, most of you probably familiar with Paul Constantine and some of the incredible work that he's been doing over the last several years. So subspace polynomials are effectively polynomials that are defined on projected spaces. And there's obviously a lot of important motivation for that. Bayesian polynomials. I'm now on the Bayesian bandwagon. So at this point, I take everything and try to make it Bayesian. So that's the same idea here. We have Bayesian polynomials, which are effectively Gaussian distribution, Gaussian processes, but with orthogonal polynomial type kernel functions. We have co-regional polynomials, which is still kind of up and coming in terms of a research idea, where you have two similar polynomials. A really good example of this is efficiency and pressure ratio. If I'm trying to create a surrogate polynomial model for efficiency or pressure ratio, surely they're similar because efficiency obviously is a function of the pressure ratio. So that's kind of the idea to some extent behind co-regional polynomials. You're looking at two very related quantities of interest. Sparse polynomials, which basically imply that a lot of the coefficients are zero. Yeah, and it's all in equadratures. We're just shy of 30,000 downloads, so I encourage you to download just so we can hit 30,000 if anything. But obviously, do look in through the code and the tutorials and whatnot. We've primarily benefited through 6 really strong academic partnerships. So Stanford, Cambridge, Turing, Imperial, University of Cagliari in Sardinia, and the University of Utah in the States. We're also an affiliate project of the Non-Focus organization, which I'm sure all of you are familiar with. And we really do try to adhere to that tagline of better code equals to better science. Okay, just a bit of a historical lesson. And once again, I realize that this is slightly different from kind of your standard workshop template, but I figured because it's virtual, it's really tough to, we tried this in full disclosure, tried to have like a full-on workshop with active coding, but it's very, very difficult because it's tough to help out people with the code when we can't be physically behind you, if that makes sense. So yeah, I'm just gonna talk for a bit more. Okay, so in the early 2000s, there was this focused interest on the idea of what we now know as UQ, but quantifying the uncertainty in computational models. And I note here two really good books or 2 really good references. And it was really Dongbin Zhu and his advisor, George Karniadakis, who started this used the term polynomial chaos to refer to this idea of having a physics-driven model where your inputs were characterized by some sort of probability distribution, and you wish to determine what the impact of that uncertainty on your output or f of x was. And so the idea, as I'm sure you're all familiar with, was that you evaluate your complex model at a few quote-unquote quadrature points, and then you construct a polynomial through those points. Now, the science of it is really that you choose the points or your design of experiment, if you will, based on the underlying probability distribution. So there's almost a very strong relationship between the distribution of the points that you would pick and rho of x. You can do this in multiple dimensions, and the simplest way to do that is just you take your grid that's in one dimension and you tensorize it, and you basically get a tensor grid. You can do this in 2 dimensions, and obviously it extends to as many dimensions as you want. The nice thing about this, and this is why I've always been a huge proponent of polynomial chaos type techniques, obviously only if your function is smoothly varying, because once you've generated a polynomial, you literally have the power, right? So you can easily compute mean, variance, skewness, and kurtosis. You can compute probabilities of the output, sensitivity indices, which often enough are, if there's any utility in the code that's been used more than some of the others, is just the calculation of Sobel indices, which using polynomials or orthogonal polynomials is incredibly straightforward. You just start to inspect each of the coefficients that you have. Actually, if you have a polynomial that's well constructed, you can exploit its gradients. Gradients are easily obtained, and that can be used for design optimization efforts. And in fact, in equadratures, we have an entire library of optimization algorithms that are built on this idea. I want to emphasize one thing, because for those of you who are not familiar with this, you might be asking, well, what is the relationship between the coefficients of a polynomial and this integration that we have, or this grid? So the idea is really simple, and it goes back to, well, almost a Fourier series, right? So if you think of a Fourier series, you effectively have f of x is equal to a sine of something plus b sine of something plus d cosine of something, et cetera, et cetera. So the coefficients here are the a's, the b's, the c's, the d's. Now, what you recall from when you first learned about a Fourier series was that in order to determine what the coefficients are, i.e. the a's, the b's, the c's, you'll recall the formula is something along the lines of a is equal to the integral of my function multiplied by sine theta d theta. B is equal to the integral of my function multiplied by cosine theta d theta. So the point is that each coefficient is actually an integral, right? In order to determine the coefficient, I actually have to be able to integrate over the space of the function. And so that's why for constructing these polynomials, we need to sample over the space of the function, over its domain, and that sampling is done using some sort of a numerical quadrature rule, with the idea that we have almost a guarantee on the accuracy of the coefficients that we obtain. Now, the caveat here really is that the number of points you see correspond to how many times you evaluate the model, right? And we like to reduce that, but it's almost like you're trying to be a miser in terms of you want to evaluate your model the fewest number of times, but at the same time, you want the highest accuracy in the coefficients that you're trying to capture, right? So it's, I mean, in order to get one, you have to give up the other. So in terms of a research problem, there's been a lot of interest on trying to reduce the number of quadrature points or coming up with more precise numerical quadrature rules, especially in high dimensional spaces under different distributions. And like I said, there's usually some sort of a trade-off between a reduction in the number of times you have to evaluate the model and the accuracy of your coefficients and the number of coefficients. And in fact, effective equadratures started, where the name is actually born from this paper that I co-wrote with Akhil Narayan and Sankar Mahadevan, which was titled Effectively Subsampled Quadratures, which is basically how we can use linear algebra to identify new quadrature rules, especially for high dimensional integration. And as with most research efforts, I realized quickly after I wrote that paper that, you know, there's a lot of other stuff you can do, right? So you don't necessarily have to try to generate these kinds of designs of experiment in 10 or 20 dimensional spaces, primarily because of one really important observation. And that is this. So Paul has, I think he's quite infamous for having a chart like this, where he has number of parameters and the number of points per dimension. And if the running time for a single evaluation is a minute, this is how the scaling goes. So one parameter, I have 6 minutes. 2 parameters, the amount of time it's going to take to run the models is 36 minutes. 10 dimensions, just in terms of time, it'll push you back to World War I, and 50 dimensions, it pushes you back to the Upper Paleolithic period. So that's just, if you started today, like, how many years would it take for you to finish your assignment? And that obviously is something that we're all quite familiar with, is cursive dimensionality, i.e. my model has too many parameters. And so in order to abate that cursive dimensionality, there are a few tricks that we can use. And that is kind of embodied within the code in a class called Subspace, which is all about the construction of subspace polynomials. So as promised, since this isn't really a real workshop, there's a bit of math here. So this is effectively what we've been doing up until Paul showed up. Obviously that's perhaps that's too broad a generalization, but let me rephrase. Before I was introduced to the subspace-based dimension reduction, this was my worldview, that I have a function that's effectively represented well by a polynomial. And then after reading a few papers by Paul, namely his book on active subspaces, and then we've been working with him on this, I came to the understanding that there's significant advantages in characterizing your function over a subspace. So f of x is approximately equal to p of m transpose x, where m is a tall matrix, and the idea is that, let's just give some numbers here because it's probably easier to digest. So if you imagine d is 25 and k is 2, so rather than constructing a polynomial in 25 dimensions, which has 351 unknowns, there are 351 coefficients in a quadratic in 25 dimensions. So that's a fun fact. In 2 dimensions, there are only 6. So quadratic in 2 dimensions only has 6 coefficients. So naturally, it makes more sense, if you can, to construct these polynomials over subspaces as opposed to the full space. Here's just a quick example. If you're interested in replicating these results, the data for this is actually available online, and I think we even have a tutorial to this effect, where we have effectively a Rolls-Royce fan blade. Obviously, the data that you find online is all non-dimensional, but yeah. So you effectively have this fan blade, and the data set is characterized by some sample points x, which would effectively be 350 different designs. Each design is characterized by 25 design variables. And for each design, we also give you the efficiency value. And the exam question really is, can you identify some sort of low-dimensional subspace for said problem? Just to give you a bit of intro, if you were to just take this data and project it randomly, this is what you'd observe. So I'm taking each row in this data set of the different designs, each x, pre-multiplying it by m transpose, which is where m is 25 by 2. And if m is selected completely randomly, this is the kind of result you observe. And again, for another randomly generated m, and again. So there's absolutely no structure in this data when you project. And the idea behind data-driven dimension reduction is to identify an m that minimizes some sort of a objective, typically the error, as you project this high-dimensional data onto this low-dimensional subspace. So just a snippet of code. If you use effective quadratures, which you can install, by the way, easily using pip. So for those of you who do want to follow with code, feel free to do so. You can, within 4 lines of code, you effectively will be able to generate a subspace polynomial. When you do this, the m that you get out of this can be used to project the data. And if you take this fan data set that we have online, this is the result that you'll get. So we've effectively taken the data. So this is a real safety data that's 25 dimensional projected. And we identified that there's this dominant 2-dimensional subspace on which efficiency is basically a quadratic, which was a really, really nice result. Side note, there's a really strong aerodynamic reason why you observe a quadratic trend. And I'll give you a paper reference later on. So this is something that when I first saw, I kind of fell off my chair because I thought it was really exciting that, and when you get these results, you tend to, go overboard. And I told myself that, wow, that, Rolls-Royce has been optimizing using this 25-dimensional design space for years. And now it turns out that, their fan blades admit this dominant 2-dimensional subspace. Therefore, they don't need to optimize in 25D anymore. They can just optimize in 2D. So you can replicate that very result using the code. It's just a side view of the same thing. Now, the nice thing is once you have this projection, naturally you can fit a polynomial over this. And the idea is that that polynomial then serves as a surrogate, not only for optimization, but perhaps more importantly for sensitivity analysis. And this is where things get interesting because you can use the coefficients of this projected polynomial to infer what the sensitivities in the full space are, right? So although you've constructed this polynomial in 2 dimensions, you can figure out, or estimate rather, what the sensitivities are with respect to the original 25 parameters that you have. And once you have, it's the same idea as before, once you have a polynomial that's constructed, whether it's over a hypercube or some sort of a projection of a hypercube, you can easily compute these quantities as mentioned before. Okay, so perhaps it's worth spending a few more seconds on this idea of splitting the space, because that's effectively what we're doing, right? We're identifying a subspace along which efficiency is very dominant. Now, if you just think about that for a second, that implies that there's something else out there where the efficiency is not dominant, right? And we can exploit that mathematically, or explore that mathematically as follows. So we write x is equal to the identity times x, which is natural. And then we break the identity down into m and its orthogonal complement. So it's just worth bearing in mind that m, the columns in m are actually orthogonal to each other. And so that corresponds to 2 of the 25 directions. And then there are the remaining 23 directions that are that fall in n transpose. So m transpose represents the active subspace, and then the idea is, can we exploit this space for design? And as I mentioned before, we've published a few papers in this space, not just on fan design, but also temperature probe design, on how you can exploit the active subspaces for design. And it's not just about efficiency, but for the fan test case, we looked at fan performance at multiple speeds, and we looked at different fan blades as well. And we did a really detailed analysis of how the subspace varies as you go from low power to high power, or if you look at transonic fan blades versus low speed fan blades. So there's really a lot of information you can extract by just studying these subspaces. And then more recently, we've been interested in the inactive subspaces, and the rationale for that has been if you think about it from a manufacturing perspective, you'd like to relax the tolerances on the inactive subspaces or designs that are sampled from the inactive subspaces, because for a fact that variation in the inactive subspace will not alter efficiency, will not change your performance. So the idea that we're playing around with was, how do we exploit that? And I won't go into too much detail, but we wrote a 2-part paper on this topic. So this was done by my PhD student, Chunyi Wong at Cambridge. So it's called Blade Envelopes. And it's all about how you can exploit the inactive subspaces, both for scalar valued outputs. So with respect to our case study, we're looking at the von Karman Institute LS89 turbine blade. And we were studying both pressure ratio, flow capacity, and loss, so pressure loss. So those are scalar value quantities of interest. And in tandem, we're also looking at the isentropic Mach number distribution, which obviously is a vector valued quantity. And this is what we came up with. So if you look at the paper, this is what a blade envelope is. And it's basically a statement about how you should design for manufacturing. More specifically, if you take any profile from this distribution, and it's literally a distribution that we sample. So you have the nominal blade, which perhaps is a bit tough to see in this picture, but there's a nominal blade, and then all the purple and green profiles are just samples from a distribution, and we're basically guaranteed that any sample you generate, any of those purple or green profiles, will have the same performance as the original LS89. In order to explore the inactive subspace, if you wanted to do it in code, it's really simple. It's just one additional line. Once you have discovered M, N is simply the null space of M transpose. So it would return a 25 by 23 matrix, and then you exploit this matrix for generating things like blade envelopes. And it's just another image. If you wanted to do this for your own blade, for those of you folks who do design, we actually have, quite recently, we wrote on Discourse. You'll find a blog article about how to do this. So we basically take, for this result, we basically patch in SU squared, which is open source, Blender, which is open source with our code, and we generate these kinds of graphics. And the hope is that for, future compressor and turbine designers, if they wanted to understand what the impact of manufacturing is, what kinds of tolerances they should impose on the design in terms of manufacturing, they could literally 3D print a blade envelope and have it sitting on their table, and they could study the distribution associated with the envelope. So this is something that we shared as well with Rolls-Royce, and they were really happy about this. And there's even, they actually want to generate such envelopes for in production blades, just to understand the impact of manufacturing variations. So this is something we're really excited about. But yeah, the code's all open source, so feel free to use this on your own test case as well. Okay, the next capability that I want to talk about in perhaps a bit of detail, and that's largely because you guys are at VKI, and this pertains to VKI stuff. So yeah, it's this functionality of a Bayesian polynomial, which is also in one of the more recent feature branches of the code. And loosely speaking, a Bayesian polynomial is actually a Gaussian process with where the kernels are actually orthogonal polynomials. So in doing this, the idea is that we want to almost take the best of polynomial chaos as a methodology and adapt it to some recent changes in the way we think about computational models and the uncertainties therein. So just to be a little more concrete, this is kind of the paradigm that we're quite familiar with, where we have an uncertainty within our computational model, and we're interested in determining what the output of that uncertainty is. But as of late, and perhaps a lot of you, and some of you might even be doing research in this space, there's been a lot of interest on looking at uncertainties in CFD, among other models. But within CFD, the idea is that my Reynolds stress tensors have a certain inherent uncertainty, and there's been work on looking at uncertainty in the Reynolds stresses by an eigendecomposition, via augmenting the turbulent kinetic energy, and so on. And so the essence of that research is that you can have a workflow where, rather than having a single CFD valuation, you have an ensemble of CFD valuations corresponding to fixed condition. And so naturally, that means that f of x now has a distribution for a given evaluation of the model. Then there's this other observation as well, that at the end of the day, the best computational model need not necessarily corroborate with the experimental data. In other words, there might be a discrepancy between the best CFD model that we have and experimental observations, as is the case, as you'll see shortly, for the LS89 turbine cascade. So although it's been obviously many years now, I still think that this is quite a noteworthy test case for a variety of different reasons. So this linear cascade was tested for different Mach, Reynolds, and turbulence intensity values. And the reason I was particularly drawn to this is the discrepancy between CFD and experiment. So this is the discrepancies for the surface integrated heat transfer, so those values, and you have the experimental reported values in CFD, and the here was done with SU squared. We even explored different models within the CFD, so transition model for trying to get better surface prediction, but oddly enough, that gave us worse results. So this is just kind of the standard SU squared result without a transition model. So while not 100% physically emulative, it gives us a good place to start. And let me be a little more precise in the next slide. So the objective really is to get a polynomial model to accurately fit the experimental data. Now, as I mentioned before, we have three parameters: the Mach number, Reynolds number, turbulence intensity values. And if you try to fit directly to the experimental data, this is kind of the scatter that you observe. So on the horizontal axis, the experimental value of the surface integrated heat transfer, and the vertical axis shows you the polynomial prediction, trying to separate testing and training. Quite a bit of scatter. Now, in equadratures, we have these Bayesian polynomials where the logic is the following. We try to use, you build one polynomial and you use the coefficients from that polynomial as the prior for the next polynomial model. In other words, the coefficients of the next polynomial model will use as prior the coefficients of the model before, and so its posterior will be informed based on the prior and subsequent observations. If you do that, these are the results you get. So the only difference really between this plot or the methodology behind this plot and the one before is that here we exploit the fact that the coefficients from the CFD, while the CFD is inaccurate when compared to the experiment, the coefficients still have some information. So we use those coefficients as a prior for the polynomial that we design on the experiments, and it's the posterior of that experimental polynomial that's informed by the prior of the CFD polynomial that gives us the result that you see over there. It's a very different way of thinking about multi-fidelity polynomials, because typically what's done in literature is folks tend to minimize some sort of an error function. So you have your higher fidelity polynomial or model minimizing some sort of an error between your low fidelity and your observations. Whereas here we're taking a very Bayesian approach to the problem, which is we focus on trying to get better estimates of the coefficients rather than trying to minimize some sort of a model error. But the consequence of that is you do minimize the model error, as you see over here.
Quick question, if you can go back. So let me, essentially you have your CFD, so your model, then you approximate it by a polynomial, right? And then you take these coefficients as your prior to build a polynomial on the experiments.
Correct.
Okay. And how do you get the prior? Because if you have a value for these coefficients, I guess you just assume some variability around them, or are you quite loose in this?
Absolutely. So we assume, so we start off with, so we do it, rather than doing 2 steps, we do it in 3 steps. So we first assume a prior for the coefficients. This is a standard normal prior for the coefficients. Then we use that in a Bayesian framework to determine what the posterior coefficients are for the CFD model, right?
Mm-hmm.
And then we take the posterior coefficients from the CFD model and impute that as the prior for the experimental polynomial fit. Okay. So, the one thing I suppose I didn't report was that rather than trying to, so the initial step is that we inject a standard normal distribution as the prior for the CFD model.
Mm-hmm. But the CFD model hasn't been calibrated before, meaning you are not using the data twice. That's basically my question. No,
we're not. We use it. So there's kind of the initial prior, which is uninformed from any data. Then there's the CFD model, which obviously takes in only the CFD data, and then finally the experimental model, which takes in the experimental data. So you at the different levels, your observations are different. That's correct.
Mm-hmm. It's very impressive. I mean, it's very impressive the accuracy then that you get.
It's really surprising. Yeah, and it's just the idea of not looking for an error function, because there's a paper in CMAME a few years ago about multi-fidelity polynomial approximations or polynomial chaos, and that was and not just in that paper but other papers referenced, that seems to be the theme, that when you design multi-fidelity workflows, you're trying to find an error function, but rather than think of it that way, we've basically thought of it a slightly different way. If you need more information about this, if you need the codes to generate this result, feel free to let me know. I can send you the code that replicates this.
Okay, thank you.
Okay, I'm just going to go through the next stuff very quickly, but it's just an extension of the idea that I shared with you before, that you have these high-dimensional functions admit low-dimensional subspaces. You can take that idea and not only look at scalar value quantities, but vector value quantities as well. And so this is stuff that my other postdoc, actually Siliso, has been doing. So we think of a 50-dimensional problem, namely an airfoil is parameterized by Higgs-Anning bump functions, and we're interested in the velocity or pressure at each node of the flow field. Now, what we've done effectively is create this design of experiment where for different designs you have different velocity and you basically have VTK files associated with these different evaluations. And before I share you the results associated with the code, perhaps it's worth mentioning a few things about kind of the state of the art. So there's been a lot of work on looking at convolutional neural networks for estimating the flow field. So the idea is if you have a few VTK snapshots of one or multiple flow quantities of interest, you can create or train a neural network that then can determine for new geometry what the static pressure contour should look like, as an example. So we want to do a comparison between a CNN type approach versus our approach where we construct effectively ridge functions at each node of the flow field. And here's the high-level idea, is that these ridge structures are observed even at each node. So it's not just something that you observe in 1D or 2D integrated quantities, as we usually do. So for instance, usually you'd find such dimension-reducing subspaces for the lift-to-drag ratios, efficiencies, but those are all inherently integrated quantities. But you can actually find such structure even at the local node level. And so we find that and we exploit that to construct this kind of a vector-valued ridge approximation where each ridge is slightly different. But you don't have to do this at each node. In fact, in a recent paper, we talk about how you can leverage the fact that neighbors close to a given node will probably admit the same subspace. And the intuitive reason for that is because as the geometry varies, nodes that are close by will probably be driven by the same, in this case, Higgs-Anning bump functions that are closer to where the node is, as opposed to nodes that are, design parameters that are further afield or have an impact on nodes that are further away. So that's why this kind of structure works. And basically, this implies that for a completely arbitrary design, you can predict fairly well what the entire flow field should be. It's a bit tough to see here, but you can kind of see this very slight difference between the contours, which here try to show you the approximation. So in other words, we use this embedded structure, this ridge structure, vector-valued ridge structure, to figure out for a new design what the contours of velocity in the x direction should look like, and then we compare them with the actual evaluation, the CFD evaluation that we then run subsequently after. And this is just a head-to-head comparison with CNN. So this is a state-of-the-art network, and this is what you get using a series of stacked polynomials. So granted, the computation time for hours is a bit longer. I think it takes about 45 minutes on a single laptop versus I think you can train, depending obviously on the access to compute you have, you can train these CNNs really, really quickly. But in terms of error, obviously, the story pretty much tells itself, at least for this isolated test case. So we're really excited by this, and if anything, it warrants further research into not only how this scales and how this would generalize to flows that have shocks, etc., but also fundamentally, are there any parallels with what the weights that are actually computed at each level of the CNN can we do a comparison between some of the weights that we get, i.e. the ridge structures, versus the weights you get upon training with this CNN architecture. Okay, I'm just going to skip over this. One of the more relatively recent additions to the code has been this idea of having piecewise polynomials. And so what we've done is address a deficiency in some sense. So this is kind of your classical deficiency if you're trying to approximate, as I alluded to before, the CD versus Reynolds number curve with a polynomial. Now, why you would do that, obviously, that's a different issue. But if you were to do that, you'd basically struggle to some extent because you need a significantly higher order polynomial to fit through the curve as you see it. And so what we really wanted to do was to see if we could generate a piecewise polynomial that can then explain certain regions of curvature. So for instance, if we know from 2 to 3 the flow is pretty much laminar, so you maybe just need a linear model, and then from 3 to 4 and then 4 to 5 we have a transition and subsequently turbulence. So can we have a multiple lower order polynomials that explain the observations better than having a single very high order polynomial? And the reason we're interested in that is because obviously depends on the placement of the points, but for data sets that you typically get on Kaggle or other sources, or indeed data that's collected randomly, the placement of the points is not ideal for constructing polynomials. And so what ends up happening is you tend to get these spurious oscillations, and you see this here, especially for order 7 and order 11, where towards the ends of the domains you have a massive overshoot in the mean. And what you'd ideally want is that you'd want the polynomial to fall on that dash curve you see over there. Instead, it overshoots, which is obviously a well-known problem with polynomial approximations. And so that's basically the motivation for piecewise polynomials. With respect to piecewise polynomials, we've centered our approach using decision trees. So the idea is that you split your domain using some sort of a decision. There's some sort of an objective function that you train to ascertain where you need to generate the splits. And this is kind of your classical cart decision tree, the way it splits the domain. In a cart decision tree, as I'm guessing some of you are aware, you effectively split the domain, but you just have a single value, as you can tell from this tree, between the different nodes. So what we'd like to do is combine the utility of orthogonal polynomials and equadratures with this idea of splitting via cart decision trees. And this is kind of the high-level aspiration, that we would identify the splits based on some physical observation, some physical change, and perhaps a curvature. And we've implemented that. So if you do pick up the latest version of the code, you can use polytrees. You set, I think a lot of the parameters in terms of the number of depths, the number of levels, the order of each polynomial are set automatically, and some of them are iterated upon, so you don't have to worry too much about specifying these quote-unquote hyperparameters. And you can just basically take your data, plug it in. We have a variety of different loss functions. The one we recommend is kind of the default one, which is the loss gradient one. So this is the one that we've found the best results with, and it performs really well. So if you wanted to fit a second order polynomial to some data, this is kind of the results. Whereas for the same data set, if you fit a first order polynomial, obviously the output's different, but it makes sense with respect to this loss function that it's evaluating. There's a good example of this. This has nothing to do with aerospace engineering, but perhaps more with classical data science efforts. So this is how we use these polynomial trees for understanding house prices in California. So if you ever were interested in that, I think there should be a tutorial of this. Either it's available or it's coming out shortly. And the idea is we identify the splits between these different polynomials, and for each polynomial we exploit the fact that we can compute Sobel indices, because each polynomial is orthogonal. We can easily evaluate Sobel indices, and therefore tell you that in each region, what are the inputs that are important. And so here, for this housing data set, clearly you see the contrast in the Sobel indices across medium income, average bedrooms, and average occupancy, depending on the latitude and the longitude of the district in question. I'm going to skip over this, but this is a more kind of CFD-driven application where we're trying to we train the model to address the stress discrepancy between RANS and LES effectively. And this is a comparison with decision tree. I want to just remark that this isn't a heavily optimized network. We played around a bit with a number of layers, but presumably there are more bells and whistles that you can vary to get a better estimate. But with polytree, just using the code as is, this is the result you get. So it's quite useful to have a tool that is able to deal with data that's inherently discontinuous, and it can even take this data set and actually get pretty decent prediction values. Okay, I'm just going to skip over this, but as you can tell, there's a lot of inbuilt capability with respect to polynomial trees that we have. Yeah, with that, I am up for any questions. Hopefully this has been useful to give you some sort of an idea of the capabilities in the code. And I do encourage you to check out our Discourse Forum and tutorials and documentation. Also, if you click on the research page, which perhaps is worth sharing as well, so a lot of the stuff that I mentioned with respect to some of the research that we're interested in. So hopefully you see that. Yeah, so there's on the website, there's a research page as well. You can even watch a video of blade envelopes if that's of interest. So hopefully there should be something for everybody in terms of whether you're looking at design, whether you're looking at more traditional UQ problems, whether you're looking at surrogate-based design optimization. There should be something for everyone. And some of these, as you can tell, some of these items in this list. So we have different, depending, like if you're interested in data-driven dimension reduction, there's even a blog post and in some cases even slides for some of the different publications that we have. Yeah, and the Discourse Forum is quite hot and happening. So obviously my internet, yeah, okay, fine, brilliant. So yeah, so do check out and feel free to sign up and contribute. Even if you just have questions really on how you can use the code for a certain purpose or towards a certain need, just feel free to drop a message, and we'll get back to you.
All right, thanks a lot, Pranay. That was super interesting. I will for sure be using it because I deal with fluid mechanics problems, so I always go to this kind of like surrogates or something. So I'm always in Gaussian process, but I've been also touching a bit polynomial chaos. So for sure, I will be coming back to this. I don't know if anybody else has some question or something that they would like to ask. I know that Thierry had to go. I think he had some meeting.
I may have a quick question.
Yeah, you can ask.
Hi, Pranay. Thank you for the workshop and the talk before. So I have a question because the classical approach of polynomial chaos from Kernel-Function in CU, they assume independent variables. Do you have strategies for correlated variables in your equadrature code?
Oh yes, I'm so glad you asked that. It's a very good question, actually. So yeah, so we initially started off by looking at Rosenblatt and then subsequently Nahtov transforms to deal with, which obviously make the assumption that you have a correlation matrix. So you assume the user is able to provide marginal distributions and then a certain correlation matrix. So we did implement that, and then subsequently there's this recent paper out by John Jakeman and a few others on augmenting the underlying basis using Graham-Schmidt effectively. So not only do we have it implemented, but we have a blog post, and that's typically the way we tend to operate as a team. because there are quite a few folks contributing, we tend to make sure that if you have a contribution, that you also have a blog post. So if you just go on the Discourse, I think Nick he posted something on it's on July 20th last year. He posted new methods for polynomial approximations with correlated inputs. Am I still sharing my page? Do you see that?
No, I'm not seeing the screen anymore, but I'm following also on the.
Excellent. Right. So,
but I will have a look definitely if there is something. Okay.
Yeah. So it should be all there, and then obviously the code, and then some demonstrations as well. And I think in this case, when we read the paper, we actually wanted to design the blog post so it replicates the results of the paper. So that's kind of another, I suppose, thought process we have. If we find a paper and we go, wow, this is really cool, it'd be really nice to replicate the results, we try to replicate it using the code. And usually that involves some level of modification to the code. So, yeah, no, feel free to check it out. And if you have any bug reports or anything, just let us know.
Okay, cool. Thank you very much.
I assume that the code is in development, obviously. So you will be releasing, I don't know, new features every now and then that we could expect or something. So I guess we should keep it updated.
Yeah. So we try to do two things. About each year during the summer, we release a new version with new capabilities. But then we also have, like, you know, if you had a request that we thought would be easily achievable, we could either get like an undergraduate student to put some time to do it, or as of last year and even this year, we're going to be participating in the Google Summer of Code, which is basically this kind of worldwide event where Google pays students to code. So they get like a very small amount of money, but you know, I think it's the experience more than the monetary gain that's important. So they basically code different open source projects, and so we design projects that are amenable for an undergraduate student to code, you know, over a short period of time. And obviously, we actively mentor and help them. So if there's something that you thought would be a cool addition, that's something. Usually on Discourse, we will probably flag that up and say that for 2021, here are our projects. Even for development in Discourse on the blog, we have there's a specific criteria for things that we're doing or plan to do. So it's all there. And I think we don't send out emails, but I think if you sign up for the Discourse, you can. Well, we don't send out emails just because, first of all, just sending out emails and spamming everyone is just like more work for us, oddly enough. But then you have the option of every time somebody posts something, and it's not that often that you feel like it's spam, but maybe I'd say about once every 2 weeks or once a week, depending on people's general levels of enthusiasm and motivation, they post something. So yeah, if you just sign up for that, I think the system automatically gives you an email, sends you an email.
Okay, if nobody else wants to ask anything, then I propose we leave it here. Everybody knows now where to find your code and your tools. We've had a very nice review of everything, so I'm happy about it. And yeah, I look forward to using it and maybe interacting with you if if we need something or have some questions.
Absolutely. Yeah, no, thank you so much, Annabelle, for organizing this. It's been delightful, and then the questions are really good as well. So I'm really, really pleased.